I'm writing really slowly because I have been suffering from a rib cage pain. I hope this description is known to all of us, right? So this is a LPV system. This is class of linear parameter varying system where rho is the parameter, rho 1, rho 2 up to rho k. Now, so only difference is compared to yesterday, Monday, that we didn't consider the rate of change. So here now why we need affine quadratic stability, because there we can cover or we can consider this rate of change as well. But as you can understand that if we have to include the rate of change, then more number of constraints will come, a number of variables will also increase, right? Let's see, that is how we can accommodate that. First of all, that is this affine dependence will always be there, because for that class of systems only, that is we are doing all these exercises, okay? So now here this P, capital P or R, or the calligraphic V and calligraphic R, these are the two sets of vertices, okay? These vertices, omega 1, omega 2, W1, W2 up to WL, that is for the parameter box, and this tau 1, tau 2, this you can even write R1, R2 up to RL, that is also fine. This is for the rate of change box. Okay, so this is the only difference. On Monday we didn't consider this second box, right? We only considered the variation. Okay, so this is a polytopic uncertainty that we are dealing with. Okay, just for the revision purpose, I am first writing the quadratic stability concept, and then that is we will directly move on to affine. Okay, I already introduced that is this affine quadratic stability means earlier we had the V function that was only x transpose Px, right? Now affine quadratic stability means there not only this A, if we can think about a Lyapunov function which is also a affinely dependent function. Okay, that means then instead of only one P, if we can write a P of rho, then I mean P0 plus P1 rho 1 plus P2 rho 2. In that case, that is instead of one variable, we are bringing more variables, so that is we can do something more, or we can achieve something more compared to this. Okay, that is the concept. So in case of quadratic stability, that is our Vx was only x transpose. Maybe last day I didn't write P0, I wrote only that is P. Now I am writing P0 because immediately for the affine case I am going to write that is going to be P of rho. this is only X transpose P0 X, and the other one is that is X transpose P rho X. Now you can see that is here P0 is only one matrix variable. Okay, and what was the condition we wrote? That is this LBB system is QS. In short, I am writing QS means quadratically stable. Okay, and in the same sense, you can also write that is the LBB system is QS equivalent to saying that A of rho that is quadratically stable. The same thing. Okay.
A row the Hurwitz also.
A row, in that case we say that is A row is quadratically stable. Yes, it would be Hurwitz for all those variation. Okay, but in that case why quadratic? They use the term quadratic stability because now it is not about only one matrix, it is a family of matrices, right? But ultimately it would be Hurwitz only. So that's what I wrote, that is such that this P0 A row plus A row transpose P0 negative definite for all row trajectories. Okay, see that is here, if you write that is for all row belonging to Rk, then there is a problem. Usually that is we are familiarized in writing that all row belonging to Rk, but that means that is the entire, that is Euclidean space of k dimensional, right? But here it's a polytopic uncertainty, so it is not that it can consider any value, like it can consider there is any value within the whole Rk. So the constant is, if you see the other side I wrote, that is for all row belonging to Rk with row I belonging to, that is the constraint, row I min, comma, row I max. So as a whole, the best language is either you write for all admissible row trajectories, or you write for all row varying within the defined polytope. That is actually the full term. So here either I can write for all admissible. I think this term admissible you have already encountered in optimal control. Admissible means finite and those which are allowed. Otherwise, like in case of LQ or any other optimal control problem, if you directly write that is U belong to, that is Rm or Rk, that means any value can be taken starting from arbitrarily small to arbitrarily high. But if there is a constraint, that is it should vary within a box or that is within a window, then you have to mention that constraint as well. Otherwise, you cannot mention or you cannot show that is the U has a constraint. Say for example here, it is not that this row 1, row 2 up to row k, they can take any value they wish. First of all, their variation is bounded in between that zone, like row I min to row I max, and as a whole they vary within a polytope. So that's why when I am writing for all admissible row trajectories, that means these rows like row 1 to row k, they will vary within that defined zone, I mean that defined ranges, and also their relation would be as a whole they will vary within a polytope. Okay, so that's why either you write here or for all row like varying within a defined polytope. Okay, so for that actually we have this definition. Now that is here, what is the problem? Although it is a LMI, linear matrix inequality, but can anybody tell me that is here if we have to solve this, then where is the problem?
So same P not for all varying P's.
No, here that is we are searching for the P which will satisfy all those A within that zone. That is yesterday that is we learned that is if a row varies within a polytope, then actually that will map a convex hull of the A matrices, right? So in that way there is no problem. But here, how many LMIs? No, you see here I wrote A of row. As of now, this is infinite number of LMIs.
All the points in
That I haven't yet written. So that is actually a lemma or a theorem. This is like the definition of quadratic stability for this LBB class of systems. You see, that is what I wrote. The LBB system, or rather I could have written an LBB system is said to be quadratically stable if there exists a symmetric positive definite matrix P0 such that this holds. So that's why if you see the paper which I shared with all of you by actually Gahinet and one other author, you will see that is first they have defined the quadratic stability as well as affine quadratic stability. After that they have put a theorem or the lemma to give the ultimate result. Ultimate result means how you can translate this condition into a finite number of LMIs.
So you didn't mention the row is polytopic, that's why it is the number of LMI equation inequality is infinite, right?
No, even here also, that is if I meant, that's what I already mentioned, that is for all admissible row trajectories. That means here itself that is you are mentioning within the polytope. Now that polytope condition is required because after this, that is we can write that if and only if P0 satisfies all the LMIs at the corners. So up to this much, this is the definition of an LBB system being quadratically stable. After that, I am going to write the condition which yesterday I wrote. So one part is the definition when a system is called quadratically stable, and then a tractable LMI condition. Then this is also LMI, but this is not tractable. Why? Because now how many variations of row as a whole? Even if it is within a polytope, but if we don't have the condition of like satisfying the LMIs only at the corners, if you have to satisfy for all row variation even though it varies within a polytope, then how many points? Infinite number of points. So that's why at this moment this LMI condition is not tractable. Okay, have you understood? Then after that, that is by applying that convexity and also the polytopic, that is if and only if here again, please try to mark the difference in the notation. Monday I wrote, I didn't mention A of W. Monday I wrote in this way. That is E, A as a superscript in bracket I. That is the same meaning with this W. Here W means like W1, W2 up to is WL. They mark the vertices. So when you write that is A of W, that means one by one you will evaluate A of W1, A of W2 up to A of WL. Okay, so here how many L? 1, 2, 3 up to 2 to the power k. So here this is going to be AW1, AW2, as AW1 means that is same as what I wrote last day, like this. Okay, AW1 means A1, or here it is same like B A. Why I changed the notation? Because like finally if you go through that paper, it is only, that is, you have to read only like 2 pages there, then you may face difficulty, that is, unless I use the same notation. That's why that is I changed my notation. Okay, the same thing, only that is, it is a difference how you represent. Either you write the way I wrote last day, or else that is you mention A of W, where W denotes the vertices of the parameter blocks. Okay.
So yesterday you wrote that A of rho as some lambda multiplication by of lambdas. A rho is lambda 1 A, lambda 2 A, not rho 1 rho 2 that you have written on the.
Oh, here
Because
no,
those
here it
two
will
rows
be
are
rho only.
Those two rows, okay, there.
No, here probably that is I wrote lambda, or where I wrote lambda?
Lambda 1 into A sub 1, like superscript 1 plus lambda 2.
That is for defining convex hull.
Convex hull.
Here that is I didn't repeat that convex hull part. Okay. So this rho is the parameter, and that lambda, they are the like variables, or you can say that is parameters for defining the convex hull. That is, suppose you have like 4 points, A1, A2, A3, A4. How would you represent the convex hull of these 4 points? It would be, that is, A1 lambda 1 plus A2 lambda 2 plus A4 lambda 4, where all these lambdas would be non-negative, as well as the summation of the lambdas will be 1. Okay, so in that way lambda is the parameters for defining the convex hull. Please don't get confused between lambda and this rho. Rho is the parameter. Okay, the convex hull part came into the picture because I wanted to show you the mapping. That is, of course, when here we are considering the uncertainties or these parameters, they are varying within a polytope. At the end, that is, they are working on the A. So this, at the end you will find that is this A matrices will definitely form a convex hull. So that's why that is ultimately this result will hold. Okay, so that is only the difference. And here, that is, what is the difference in the notation? Earlier that is I wrote A superscript I in bracket. Now that is I am mentioning this A of W. That means A evaluated at those vertices. Okay, that is the meaning. AW means the A matrix evaluated at the vertices. Say for example, if there is 2 parameters, W1 means the vertex where lambda 1 mean, lambda 2 mean. Okay, so A evaluated at lambda 1 equals to lambda 1 mean and lambda 2 equals to lambda 2 mean. That is the meaning. Is it now clear to all of you? Fine. Now, what about quadratic stability? Just you think about that if P is now replaced by P rho, so you have now, you no longer you have only P0. You have now K plus 1 matrices, right? Earlier you had only P0, now P0, P1, P2 up to Pk. So as I put K plus 1 variables. Now, how can you now translate into like, first of all, you tell me that is what will be the definition for affine quadratic stability, and then we have to think about that whether in case of AQ base we can find a tractable set of LMIs.
Tractable means solvable.
Tractable means like not only solvable, finite number of. So first you have already understood quadratic stability. Now in case of affine quadratic, you have understood why this is called affine quadratic, because P has been replaced by P rho. Now what can be the formally definition? please remember that we are introducing the affine quadratic stability for including or for considering the rate of change of the variables, because that is one of the limitation of the quadratic stability, because here we considered the variation, we didn't consider the variation, we considered that is okay, it is a LBB system, so the parameters they can vary, or like their value would be within a known range, but they are not time varying. Okay, so now if they are time varying, so then the rate of change will also come into the picture. Then not only you have one box, now you will have two boxes, right? Then one variable is your, that is one set of variables is your rho y, another set of variables is your rho y dot, right? That is now the difficulty, that is, can you accommodate both?
Parameter also now can change with respect to time.
Yes, that is earlier, and now that is again one important point. Can anybody explain the difference between LPV and LTV system? Suppose here you have the parameters, we are calling LTV system. When it will become LTV, linear time varying, if there is a t term associated, right? But even in this way also, here, that is, we consider all these parameters rho, they are not time dependent, although they can vary within a known range. But suppose you are doing the experiment on that particular system, so this parameter varying and time invariant, the parameters although they can vary but they are time invariant. What does that mean? We suppose rho 1 of the parameters, its range is 1 to 2. Now during the experiment, it can be, that is like approximately, that is you can find that is what would be its value, maybe 1.5, 1.6, but within a trial it should not vary. That is the difference between time invariant and time varying. Here in the first case we consider the parameters are time invariant. Uncertain means what is the difference between this uncertain and time varying? That is when I am saying that is the parameter, it belongs to the range 1 to 2. That means within 1 to 2, it can take any value. Okay, suppose you are like doing experiment on the same system, then maybe like in your trial 1, you are getting the rho 1 maybe 1.5. In another trial, you are getting 1.6. In another trial, you are getting maybe 1.2 or 1.3. But within the same trial, it is not changing its value. So then it is called time invariant. But if it happens that is within the same trial, that is within a particular experiment, like as that is you are like doing the experiment and rho is also changing its value. We don't know the rate of change, but it is like changing. Then it is called time varying parameter. Now, if we consider the parameters to be time invariant, then your quadratic stability is sufficient, and that is powerful enough, you don't have to do anything. But if you consider that is your rho is time varying, then you have to do something more. Okay, that's what we are now going to learn. Just think about the situation.
Matrices are omega 1 and 2 omega L, not give tau 1 to tau 2, because if rho y is changing and it's uncertain in a parameter, it should remain bounded for the rho y min and rho y max for all I, right? Not for the tau 1.
Now tau there is just a different symbol. There you could have written R1, R2 up to RL. That is just a symbol.
So we have to use v dot also here.
Huh.
Less than like in that.
Huh. that is here, this is the V, that is I have characterized only V. After that, the stability condition will come from V dot only. Here, what will be your V dot?
So to differentiate it and then replace.
Now, right, some extra terms are going to come, right? So that's why the affine quadratic stability is like little bit complicated than quadratic stability. Okay, that is what is going to be, that is a V dot. Say for example this one, that is if I denote it simply by V of rho, then what will be your ddt of V of rho? Of course it is going to be P1 rho 1 dot plus P2 rho 2 dot up to Pk rho a dot, isn't it? Because the other, like, there is no variation in the p's, they are constant, right? P0, P1, P2 up to Pk, they are constant. So if there is any change, only in the parameter. So that's why I have written like this.
But P is dependent on rho.
Ha. That is like what I wrote, a rho. A rho, that is, you can split it into that fashion, that is a0 plus a1 rho 1 up to ak rho k. Similarly here also, I have used a p rho, that is which is affinely depends upon the parameter rho, okay? But all the components starting from p0, p1 up to pk, they are constant, no variation. And on top of that, they all are symmetric.
So x, t and x.
Right. Like this is only the part that is where I wanted to say, that is if this is ddt. Sorry. Here, what you are just going to write, x dot transpose x plus x transpose p rho x dot and then x transpose p rho dot. That is a notation, okay? P rho dot. Let's see, that is what is going to be p rho dot. Now, if you take it common, that is x transpose. In bracket, we are going to write all the things, and then it would be x. Then, what are the terms you are going to have here? The first two terms will obviously p rho a rho plus a rho transpose p rho, right? Because what is your x dot? That will remain the same. That is a rho x, right? So the first two terms, it will be really the same. X transpose p rho a rho plus a rho transpose p rho. Now here it is x transpose ddt of p rho, right? It's transpose ddt of p rho into x. Now, if your p rho is this one, then ddt of p rho, what will be that? So actually, what I wrote earlier, that was my p rho only. dot minus P0. Here you might have a confusion, that is what does it mean? If P rho means P0 plus P1 rho 1 up to Pk rho k, then you just replace rho by rho dot. Then what it would be? In P0 plus like P1 rho 1 dot plus P2 rho 2 dot up to Pk rho k dot. But here you don't have P0 because ddt of P0 is 0. So that's why the notation is P of rho dot minus P0, right? So here I wanted to write that is P of rho dot minus P0, but I didn't mention at the beginning because you might have got a confusion. So the base thing would have been X transpose ddt of P rho, okay? Into X. Is it clear for all of you? Once again, you please correct on your copy. We are going to have ddt of 0. Okay? So, originally what is the expression for 0? X transpose P rho X, right? So, that is if you take on the differentiation term by term, then X dot transpose 0 X plus X dot X transpose ddt of 0 into X plus X transpose 0 into X dot. So I have written the first and third consecutively and then the second one after that. Okay? Is it clear for all of you? So here what is the term that I am going to write? P of rho dot minus P of 0. So as a whole, in bracket you have 4 terms: P rho A rho plus A rho transpose P rho plus P of rho dot minus P0. Now, if it has to be asymptotically stable, quadratic stability means that is also one kind of asymptotic stability, right? Asymptotic stability in the presence of this parameter variation, right? That is an important point. If somebody asks you that it seems quadratic stability and asymptotic stability, they, at least as far as the LMI is concerned, they look perfectly the same. Then what is the difference between asymptotic stability and quadratic stability? What would you say? This is also asymptotic stability, but in presence of the parameter variation. That is your quadratic stability, right? If somebody asks you only asymptotic stability, there it is assumed the plant is expressed by x dot equals to Ax, unforced system. A doesn't contain any uncertainty. Now, if A contains an uncertainty, whether it is a parametric uncertainty or a structural uncertainty, then you have to go to quadratic stability. That means you are trying to evaluate the asymptotic stability, same thing, whether xt goes to the origin or the equilibrium point at t tends to infinity. Theoretically the same concept, but with the only difference, now we are trying to check that behavior of the system in presence of the uncertainty, right? That is the difference between quadratic stability and asymptotic stability. Now here, that is in which regard that is I started this. If you have to show that is the ordinarily the system is asymptotically stable in presence of the uncertainty, then it has to be negative definite, right? So if it has to be negative definite, then it is a quadratic form. X transpose, in between you have the summation of some matrices and then X. It is a quadratic form, so in between whatever you have, that must be negative definite. Now, if that has to be negative definite, that's a big problem for us, isn't it? Because we can handle the first two terms, P rho A rho plus A rho transpose P rho. Up to that, you can say that is okay. That is, if I assume that we have a parameter box, we have all the corners, then using that, like that corner concept, this P rho A rho plus A rho transpose P rho, up to that much it is possible for us to handle. Now, what about how can we handle this P rho dot? That is completely a different variable. Not only that, it may not be always an independent variable, because variation of rho dot, it directly depends upon rho. that's the main problem in affine quadratic stability. Are you getting? Now you think a little bit and you tell me that is what could be a bypass way. Now try to match with the quadratic stability, earlier what we had and now what are the changes. So what are the changes that you have got? Earlier the LMI was only this P0 A rho plus A rho transpose P0. Now the first difference is that instead of one matrix variable, now you have K plus one variable, right? Instead of P0, now you have a full P rho. P rho means there the ingredients are P0, P1 up to Pk. That is the first change. Then what is the second one? P0, that is okay. You have a minus P0 term that can be accommodated because there is nothing in the product in the multiplied form with P0. So P0 is free. So that's why P0 doesn't create any problem. But the main troublemaker is my P rho dot. How can we handle? Of course, we have to compromise something or sacrifice something to get a set of, first of all, to make this problem as a tractable problem and also to get the LMIs. It is not that exactly in whatever is there, we can find an equivalent set of LMIs where all the original properties would be maintained. That is impossible.
Consider the rate of change box now.
Now, of course, we are going to consider the rate of change, but how you can simplify this? That is the concept. But if you go for the Taylor expansion, then finally you will have all the higher order terms. Then it would be, even if the derivatives exist, but it will become further complicated. So here the approximate solution is, we are going to consider the rho dot as an independent variable. And with respect to that independent variable, we are going to bring in another box. That's why here I have defined two boxes. One is the parameter box, another one is the rate of change box. So that is the compromise or sacrifice, whatever you say, that we are going to do. So here now if you see, that is along with rho, we are going to define a new parameter, or a new parameter variable r. R means your rho dot. So here, what is the point of doing a sacrifice? Because originally rho dot and rho, they are not independent of each other. But here we are assuming that if the rate of variation is not too slow, like is not too less or very high, then that is we can split. We can see the rho dot as a different variable. So using that approximation, that as if rho dot is a new variable r. So then we are going to have the Cartesian product of two boxes. One is the V box, another one is the R box. Suppose for two parameters, V box contain 4 vertices. For the same two parameter rate of change, the R box will contain another 4 points. How many combinations? 16 combination. So if that LMI satisfies at all the 16 combination of vertices, then our purpose is served. Are you getting? That is in a simple way the concept. just try to understand that. We have one more condition that comes because of the multi-complexity constraint that I will write after that. But first you try to understand that what is a fix or what is the approximation that we are going to apply. Rho dot, that is now being considered as an independent variable, as if the rate of change that is an independent variable. So at the same time you have two variations, like two boxes. One is the parameter box, another one is the rate of change box. So one I have denoted by V, another one by R. Both of them contains 2 to the power k vertices, right? Because if number of number of parameter is k, the number of number of row dot variables will also be k. So now both of the boxes will contain 2 to the power k vertices. How many combinations? 2 to the power k, 2 to the power k, right? 2 to the power 2k or 4 to the power k.
So vertices coordinates are omega I comma tau I.
So now that is, if this LMI P rho A rho plus A rho transpose P rho plus P rho dot or PR minus P0 is negative definite, because at this moment, either after you consider that rho dot to be a new variable, then it becomes an LMI, right? LMI in which variables? Now what are the LMI variables? Not only P0, now k plus 1 number of variables, P0, P1 up to Pk. So it is an LMI with respect to P0 to Pk, but they are not tractable, because here if you have to consider all the possible combination of variation, an infinite number of LMIs, how can we come to a finite set of LMIs? Then again, by using the parametric like polytopic uncertainty and their Cartesian product, if this LMI holds at all those like combination of vertices, that means V cross R, then that is, it will be fine. That is the main condition, but along with that, in that case we have two more conditions that I am going to write, but this is the main one. Try to think about the situation, that is what I explained. I hope you have understood, that is this now, that is what is the main fix or the approximation, that you are considering the rate of change as a new variable. That is the approximation. Although in practice we cannot say that is the rate of change that is independent of the original variable. So in that way it is an approximated one. Rho bar means the average value. That means for individual parameter, if you simply do, that is rho y plus rho y mean plus rho y max by 2. Okay, so that is called the average value. So this rho bar, that is the average. Okay. Just 1 second before that, I have to write that number of variables. expressed with respect to W, that will have been appropriate. That is the notation. Why I change the row to W? Because otherwise I cannot point out that this is going to be satisfied at the vertices.
So first the transport.
Only the last one would be little bit abrupt for you. That is why all of a sudden this is coming. This is because of the multi-convexity constraint. Multi-convexity, okay, you write first, after that I will explain. The third one, that is pi ai plus ai transpose pi greater than equals to 0. This is only the condition that is which you may not, or that is apparently, that is it would be like a problem for us to digest this. That is why this is coming, or because in most of the times that is we have been familiarized to see that pa plus a transpose p less than 0 or lesser than equals to 0. But in that case, that is why this particular thing is coming. The reason is, when in case of affine quadratic stability, we are going to handle multi-convex constraint. Why multi-convex constraint? Because earlier you only have a P0. Now you are going to have P0, P1 up to Pk. So these P's, they are going to be associated with the parameters, that is rho 1, rho 2 up to rho k. So multi-convex means that is now not only with respect to P0 but with respect to all the P's, because as now there are many components of P. So, and you know that is what is the convex criteria. Suppose you have a function f of theta, and then that is if it is whether it is convex or not. How would you check? That is, first of all it has to be a positive definite if it is a strictly convex function. Positive definite, and then it is like maxima or minima, it must be there, and then the second derivative that must be greater than equals to 0, right? So from that, that is we get the condition. Now if you, this is the condition for which we are going to write, right? So if this is the function and if it has to be strictly convex, for that what would be the condition? Then you will find, that is in that paper, the proof is there, I am going to show you here only. You will find that is if we consider that is under which conditions this matrix would be negative definite, or as a whole the function will be strictly convex, and for that this third condition will arrive. That is like for the first time you are going to see why this is happening. All of you please check one by one. Multi-convex lemma, that is the lemma 3.1, and accordingly the condition will come. This paper I have uploaded to the WhatsApp group yesterday. All of you can, that is open, if internet connection is there, please download that paper, affine parameter dependently upon a function. This part is there on page 3. It is there on page 3. First you will find the lemma, probably lemma 2.1, which deals with the multi-convexity constraint and the conditions what are required. Then at the bottom of that page you will find that the proof has been done. The theorem which I have written, that is there, the proof is there at the bottom of the same page, where that condition pi ai plus ai transpose pi greater than equals to 0 is written. But why that condition comes? For that the main source is lemma 2.1. It is if f of theta 1, theta 2, theta k, if that function has to be convex, then what are the conditions? You will find the coefficient of the second power of theta, that must be greater than equals to 0. This is a small paper and you have to check only the 2 pages. Okay, you can take a printout because I think the size of the letters, I mean the one of the main problem is that it is not a good thing to read because the letter size, at least in the print, this is too tiny, right? So that's why that is even before going through, that is, it creates a negative experience for us. Hi, this is Dennis. Okay, we will get up. Monica, देखिए, तुम्हें पता था? Now, why this is important? Suppose that is, if you work with power electronic converters or the stream-mass damper system kind of things where you have parametric uncertainties and then multiple parameters like rho 1, rho 2 up to rho k, if you consider they vary within a polytope, especially in case of power electronic converters. Why? Because this R and C, of course, there will have variation because like you cannot get a circuit where even if that is you give a order to a company that is okay, I need that is 1 millihenry inductor, maybe like 10 microfarad capacitor or 1k or 10k resistor, but always we will find there will be some tolerance, right? It cannot be like perfectly 10k. Okay, so always there is a tolerance band. So in those cases, of course, there will be variation. And also when you have a circuit and you keep it switched on for suppose half an hour, then 40 minutes, 1 hour, because of the heating effect, the resistance value and the other one will also change, because inductor also contains some resistance and impurity, capacitor also contains some resistance as impurity. So as the experiment time goes on, increases, so there will be some changes in the parameter. So in those cases, really you will have to face a similar problem of like either a time invariant parameter but mostly time varying parameters. So in such cases, if you have to design a robust controller, you can easily apply this kind of analysis. So that's why that is although like it is an advanced result, but still I thought of covering this because at the end during your project it can help you. Fine. See, at this point, that is, I will pose only one question to you. So far, we have discussed a lot about parametric uncertainties, but everything in the state-based domain. Don't you have the question that is, can't we have parametric uncertainty on transfer function? Of course, it can appear, like if you remember, that is at the beginning class, I gave you the example of a simple second order k by a square plus p1s plus p0, where p0 and p1, if they vary in the same polytope or if they have independent variation, then in the transfer function domain, don't we have any robust stability result? That is the question. Here, whatever we have done for parametric uncertainties appearing in the state-based domain, if it is in the transfer function domain, then how would you handle?
Convert it to the state system and then solve it.
Well, as you know, that is like directly it is when you have in the state space, or if it is a transfer function, then once you have a parameter, then it is really very difficult to convert because it may not be 1:1 map. Even if it is a 1:1 map, but by taking the inverse Laplace, it would be really difficult to get this A row. Suppose you have the characteristic polynomial and then you wanted to convert into, that is ABC. Now what would happen, that is this row, if they are not exactly constant, right? Suppose if that is slowly varying, or even if there is, it is time invariant, but you don't exactly know where the parameter is. So it may not always be possible to directly get this state space out of transfer function. In some cases it may be possible, in some cases it may not be possible. So that's why we have to search for that, do we have a similar result on the S domain, I mean on the transfer function domain. For the same parametric uncertainties, if they appear in a transfer function, do we have any robust stability result? It must be, right? What is that? That is called an extension of Raut-Hurwitz criteria to parametric uncertainty cases. What is that? Kharitonov theorem. Have you heard? Okay. That we are now going to learn. Why that is called extension to Raut-Hurwitz? In Raut-Hurwitz, what do? You have a characteristic polynomial. You check by applying the first by
changing the sign of the first coefficient.
Exactly. Now that is, if you have a similar characteristic polynomial where each coefficient vary in a range, then that is, the concept was, or the thought was, can we develop a Raut-Hurwitz like criteria for systems where for a polynomial, I mean the characteristic polynomial, where the coefficients vary in independent ranges. That was the concept. And it was proved by one of the Russian mathematician, I think M. Kharitonov, in 1978. Not a very old result. only it seems that is how to remember, or is there any pattern? Yes, there is definitely a pattern. What is the pattern? Min min max max, that will be repeated. Then max max min min. Then min max max min max max min, and then max min max min max. Once again, min max max, then max min, then min max min, then max min max. It was a great discovery. Why? Because you see, that is, if you can show for any nth order polynomial, these if these four polynomials are all Hurwitz, then for any variation of this kind, under any variation of this kind, the system will remain asymptotically stable, or you can say Lavoisier stable. That is the Redonov's theorem. So first, consider the family of polynomials. Why family of polynomials? Because now you have a parameter here, rho, not only one parameter, that is n plus one number of parameters. So it will create many polynomials. So that is, as a whole, we call them a family of polynomials, denoted by p of s comma, not delta, it is actually rho, sorry. Because p of s comma rho means a polynomial, that is, which is not only a function of s, there is a parameter rho as well. That set or that family I have denoted by this capital calligraphic P. Okay. Now construct the four Kharitonov polynomials. These are these, and then finally, what is the result? That is, the system will be robustly stable if all this, if and only if, not only if, that is, it is both necessary and sufficient. If and only if all these four Kharitonov polynomials are Hurwitz. That means you apply Hurwitz criteria to all these four polynomials and check whether they count the number of changes. If all four are Hurwitz, then as a whole the system will be asymptotically stable. Okay. Let us take a small break. After that, we will come back.
Can you do this?
A means lower LFT. Okay. Lastly, I mentioned LFT will be of two types, lower and upper. So here, why it is called lower? Because the block which we have embedded that appears in the lower part. Now another one that is the counterpart of this thing, we are going to learn upper LFT, where there won't be any K, so it will be straight away U and Y, but we have delta on top. And then if we embed delta and if we express the transfer function T Y U, then it would be called upper LFT. That is the thing I am going to do. So you can also do.
So if we add factor, it is lower LFT, and if we
Exactly.
add the answer, it is
Huh,
upper LFT.
So here, that is what is the purpose? for whenever that is we have to do something with lower stability, we always need lower LFT. Why? Because lower LFT means it embeds the controller. And why do you need this lower LFT? Because this is nothing but TZW, or rather TZ delta W delta. So that is the transfer function, I mean the nominal closed loop system after removing the uncertainty. Now you compare with the case study or the example we already did twice, that is the case of additive uncertainty. After eliminating the delta, then the signal will be there as it is, right? One is J, another is W. We will always try to find the M of S, because ultimately we need the MS represent M delta representation, right? So nothing but that. So here ultimately what we need is MS, that is nothing but same as so whenever overstability is concerned, we need lower LFT. This expression like FL, it looks like that it is quite big, right? But there is a very simple rule to remember. Can anybody tell me? That rule we have already learned. Exactly. How? If you start from 1 1, then after that 1 2, the inverse of P22. Now here with P22 you have something, okay? So there you can think about that as if there is a K, there is a K, and so the order would be 1 1, then 1 2, inverse of 2 2, and then 2 1. Exactly in the same fashion it will be. P11 plus P12 into K into I minus P22 into K whole inverse into P21. And then when you will derive the upper LFT, you will find that it will have the reverse structure. That means it will start from P22. Then it will be P22 plus P21 into delta into I minus P11 into delta whole inverse into P12. Please complete the upper LFT part and please check whether it is done. Any problem? So in case of upper LFT also you have to proceed exactly in the same way. That is, first you write down the equations for the open loop system. I mean Z delta equals to P11S into W delta plus P12 into U. Similarly another equation for Y, and then you have the common you have the most vital equation W delta equals to delta into Z delta. These three equations we have, right? lower LFT is required for robust stability context, then why or where this upper LFT would be required? Any idea? Huh? No. For stability already we had lower LFT. Now stability or robust stability, everything that is concerned in M delta. So that's why we have separated delta, and the remaining thing is nothing but a lower LFT. Here, what you have seen, that is we have embedded the delta, and now this is a mapping between u to y after embedding delta. Then when it would be required, or what is the purpose? Why or how do you check if you have this FU? May not be robust, or rather there is a main purpose is if this is the mapping from u to y including the delta, then suppose you want to have some performance, say for example H2 performance or H infinity performance, maybe on U, like the minimum energy control, or maybe you are going for ISE, integral square norm minimization, so you have some constraint on E. So ultimately, that is, you have to check that is what constraints we originally we consider while designing the controller. Finally, whether this FUP delta will satisfy that performance in the presence of delta, that is the purpose. Are you getting? That means when you have this mapping, that is, this is nothing but TYU in presence of delta, so you have to check maybe the H2 norm or H infinity norm of this TYU in presence of delta. That means counting the delta within the admissible family. That means for this any delta within a family for which you have designed the controller, whether finally it is satisfying the performance in presence of the delta. That is the requirement, or that is the purpose.
What you have told that some finite H infinity gain is there for delta. So we have to recheck it through upper LFT.
Sorry, one second.
Like delta should be less than some finite in H infinity finite gain. So we are checking it through the
Right. So for that, actually, that if I say that is the you first define the set of delta. Can anybody tell me that is how to define what I am saying? Well, if you say that is an admissible delta, what does that mean? That means delta must belong to the set you have defined and for which you have designed the controller. Now that family of delta, how would you define?
Delta norm of H infinity less than equal to gamma.
So suppose if that set is capital this one, okay, how would you define? That this is a set of all delta which belongs to RH infinity, suppose n cross n, again for simplicity I am assuming a square system, such that this is called the set of uncertainty. Now if I say something that is okay, I need to test this performance in presence of delta, then in presence of delta means all the admissible delta. What does that mean? That is, you must check the performance in presence of delta where delta varies or delta lies within this set. Okay, that is the meaning of all delta. So here actually this delta belongs to capital lambda, and here, like, probably that is you had some confusion, that is like how these things is going to happen. Actually we do this after taking the lower LFT. That means suppose first you have already taken lower LFT, okay, then after, like this K is already embedded, then you are bringing the delta. So here that is I am giving a bar, P bar of S. P bar of S means that is actually, that is you have already embedded delta, so you have got FL. Now with that FL you are connecting the delta, so then you can find out TYU. that is actually the purpose. Immediately you will ask that is sir, this is like ये तो थोड़ा उल्टा पुल्टा हो रहा है, क्यों हम लोग को वो p bar of s चाहिए? Any case?
Controller is embedded. Now it is not the simple plan. It's also.
क्लोज लूप में कंट्रोलर चाहिए ना, तो इसीलिए p बार लिखा।
But FU, actually this is the purpose of like finding FU and testing with FU. For that is why you need p bar. Why not simply p?
p is open structure है और क्लोज लूप स्ट्रक्चर में a को इवेंट करने के बाद p बार हो जाता है, तो क्लोज लूप विद अनसर्टेनिटी को हम लोग करते हैं।
That is, in simple words, when you are checking the performance of a system, do you check the performance of an open loop system or closed loop system? Of course, closed loop. Now, closing the loop means embedding the K. So that's why if you have to test the performance, first you have to embed K. That means you have to close the loop. That's why the first requirement is that you close the loop by embedding K, which is nothing but FL. So finding FL means you have got M of S, right? So up to when you are finding f of L, we have simply kept aside delta, right? Because up to that much we were checking only robustability. Once the robustability part is over, then you have to just verify the performance. Like what verify the performance means, you have designed the K not only subjected to robustability, also some performance criteria were also there, right? So now ultimately it is your responsibility, I mean the responsibility of the control designer, that after designing the KS, you plug in the KS, you find the closed loop system, and then you check the closed loop performance not in the absence of delta, in the presence of delta. That's why finally, that is, we bring the delta into the picture and we close the loop from our upper side.
That means P1112.
Now they are all as if P11 bar, P12 bar, P21 bar, P22 bar. So here during the derivation, I didn't consider all those facts. I have separately derived lower LFT, upper LFT. So that's why whatever you have written so far, there is no error. But now if you have to explain the purpose for finding FU, then you need all this additional information which I just explained. Once again, I have derived the FL and FU separately. So there you don't have to write P11 bar, P12 bar. Individually they are correct enough. There is no error. But if you ask, that is finally what is the purpose? Now see, here if I find is T, Y, U, then of course I have embedded the delta. But from Y to U, the loop is open. Do you wish to test the performance without embedding K? Of course it is not. Once you embed K, that means like at the very beginning, you have closed the loop. So it is no longer, this P no longer the original P. This is another P. That's why I have written P bar. Have you understood? Exactly the thing, that is, any of the examples we considered earlier, just try to think about the situation. Now, that is, we will, like, this robust performance will come at the very end. Like, before that we will learn, especially after this, our purpose would be to learn the edge infinity controller design, especially LMI based edge infinity controller design. So now that is, I'm going to show you that what kind of problems you can expect in the exam. Okay, so the case one, like case study one, was when we have considered the uncertainty in the additive format, right? Case 2 was maybe output multiplicative, then input multiplicative, after that inverse. For each of the cases, like there can be like most expected type of question is that on the diagram I will mention the W as well as Z. Don't worry, that is now only that is I'm going to take one example. So here the block diagram would be given on the question paper. The plant and the controller uncertainty, all of them would be mentioned. Z, delta, Z, W, all of them would be mentioned. And then you will be asked to find out that T, Z, W or I mean the MS, both in the frequency domain and time domain. Are you getting the question? That means for the case 1, by hand driven calculation we already found M of S, right? After that we learned how to write P of S. Last day I already told you that is M of S is nothing but this one. So if you can write down the expression for P of S, then even without doing all those hand driven calculations and substituting the variables one after another, directly this will lead to finding MS. That is called finding finding the M of S by applying LFT. So now see, this is possible both in frequency domain as well as in state space, because for PAC we have already seen that is the transfer function representation means the 4-block structure 1 1 P1 1 1 2 2 1 2 2. The same thing in the state space also it is possible A B1 B2 C1 C2 D1 1 1 2 2 1 2 2. Now if somebody asks you to find out MS, it is possible to use both the frequency domain approach as well as the state space approach. So in the exam you can expect that is I will ask you to find out the MS corresponding to a block diagram, and then I will ask you to verify the relation through the other type. So if you find that in frequency domain, you have to find the state space from the same thing from the state space domain and get back the same transfer function. Okay, let's see that is what does that mean. Can you first write down the generalized plant both in frequency domain and state space? this will be the 4 block structure, right? So now accordingly we have to find out P11, P12, P21, P22. For that, what is required? That is this expression for all this delta Z1, Z2 and E with in terms of W delta D0, R and E, right? So these 3 together it is Z and these 3 together is W. That is we already learned that this may not be a scalar, that is it. And here you can see that is we have 3 objective signals. Why 3? One is Z delta, which is entering into the delta block, that is one objective signal, and I have defined 2 more. One is the U, another one is the YM. You can analyze why you are doing so. I need Z1 because I have planned to impose some performance on the error signal. So that's why I have designated the error signal by Z1. Okay, and then for disturbance attenuation, I have to do something on YM. That is the reason why I designated that one by another Z, that is Z2. Okay. If you, in addition, if you have to do something on U, then that is you may declare this another signal here by Z3. That too you can do if you have a plan to impose some constant on the U as well. Okay. So now let's write down the equation. That is first of all here what I need. Z delta of S, that is U of S. Fine, we don't have any problem with that. Directly we are getting U. Then after that Z1, right? So what is my Z1 of S? Z1 of S equals to E of S, which is R of S minus Ym of S, R of S minus Ym of S means Y of S minus D0 of S, and then again Y of S means Y0 plus W delta, so it would be G0 of S into U of S minus W delta of S minus D naught of S, right? Then what is your Z2? Z2 of S is nothing but your Ym of S. So already we have done, so here you can write. Now, how can we write P of S? one Z delta is US. So 0, 0, 0, I, right? Then Z1. So Z1 is going to be minus I with respect to R, so plus I, and then minus G0 of X. Then Z2, this one. So I, then D0, another I. After that you don't have anything from R, so it is 0, and then G0 of this. Z1 and E, they are the same. So one is minus I minus G0 of S. How will you do the partition? Right? This will be the partition. That means this is your P11. This is your P12. This is your P22. This is your P21. Okay? Now, exactly in the same way, we can express the generalized plant in the state variable format, right? So, what extra will be there? First of all, you have to write down the x dot, right? X dot equation, then y equation, then the z equations. So, let us write that. X dot, of course, there will be an A matrix AX. A is A, B, C, D, or rather here we are going to have A, B1, B2, C1, C2, and D1, 1, 1, 2, 2, 1, 2, 2. Now for Z0, how we can write that? Suppose for the G0 you have still that is A, B, C, D. So what would be the state equation? X dot equals to AX plus B U, right? Now yes, X dot equals to in that case we don't have any uncertainty or disturbance at the input side, so this will remain BU only, no problem. And then that is if I write y means the measured output, so here that is we have to take ym, please remember that. So that ym, that is your nothing but y plus d0, and then your y means g0 plus w delta plus d0. Now this y0 that you can write by cx plus du. Here I am assuming that this ABCD is a minimal state-based realization of the nominal plant G0. Okay, ABCD is a minimal realization of the nominal plant G0. Accordingly, I am writing. Now, if you are happy with ym, then fine. That is, let us move to Z1, Z2, and Z delta. So now your Z1 means that is your error variable T. R minus ym. R minus ym means R minus Cx minus du minus w delta minus d0. Z2 Z0 ym. Cx plus du plus w delta plus d0. And finally, z delta equals to u. no further simplification is required because already A is one of the variables. Now you have to draw the structure of the generalized plant in this state variable format, right? This you have to draw and accordingly you have to fill. Okay. So what is your x dot equation? It is A, of course it is Ax. After that, how many zeros? Few zeros and then B. After that you Z delta means U. Then you Z1 R minus Cx, so it starts minus C. Then your double delta, that is minus I. Your D0 another minus I. Or do you have something for R? Yes, we have I. And then this minus E. Please check whether I didn't mistake or not. Is it 257 plus C? And then you have one I, another I. For R, you don't have anything, so it will be 0. And then finally, here it will be plus D. So that is for 2. And then E means simply Z1 is going to be repeated. So minus C. I minus I plus I. Now you have to identify A, B1, B2, C1, C2 and D1, 1, 1, 2, 2, 1, 2. So A remains the same A, no doubt for us. These 3 zeros, what are they? That is nothing but B1, right? And this B means originally, B2 means original B, right? Now what is your C1? C1 is the C matrix for writing the objective signals. So these 3 together, that is your C1 and your C2 is the original C matrix, right? These like 0 minus C plus C together they construct the C1, right? And your C2 means the original C matrix of the nominal plant. right? And then after that, so this 3 by 3 block matrix, this one, that is your D11. Then D12, D22, and finally this one is D21, right? Is it now clear? Now the verification part, which I was talking about in the exam, you may expect a similar question. If I ask you, that is, you verify this procedure for, like, first of all, MS, right? First of all, you know that is MS, what did you write? P11S plus P12 of S into KS I minus S whole inverse into P1S. So one part is the finding the FL. So if you have to find the FL, like simply you have to use P11, P122, 122, okay? And you see here, since I am asking that is MS, that is in the transfer function domain, so it would be easier to use the transfer function approach. That is P11 of S, P12 of S. So there the state space is not required at this moment. So for finding the FL, everything you can do in the transfer function domain, right? Then the verification part is that is if I ask you to verify whether this state space approach and the transfer function approach, they are equivalent to each other, then how can you show? Say for example, that is you want to verify for P11. So what is your P11? P11S means that is C1 into Si minus A whole inverse into B1 plus B11. Now you have to do that simplification. So you already have this C1 here, A remain as it is, B1 you can mark 0, 0, 0, that is your, in this case the B1 means all 0, okay? And then B1 is going to be your D11. So that is, after that you have to find out that is what is going to happen.
Same. E11, D11.
Immediately you can see that is we can verify, right? So in that way we can verify all four. So this is actually the verification, and that type of question is expected, and this is like pretty straightforward. So this is one type of question. Second is the for LMIs that we have like formulated at least 6-7 different type of control theoretic problem in the LMI, right? Like starting from this like Riccati, like Lyapunov, after that bounded real lemma, and some more. And when you will like see that book, like Boyd Balakrishnan, the 4 authors book, there also you will find some other LMIs. So 1 or 2 questions will be there from LMI based formulation of a control problem. A bounded real lemma proof, if that comes, it would be a long proof. There is only one question, 7 marks or 8 marks. So in this part, like especially in the post-mid-sem part, most of the things are derivation kind of thing. Only there is a numerical question, means here you can expect this kind of numerical. This is still not numerical. Something derivation, but with the matrices, you don't have any specific like numbers, right? Only numerical problems can come from the Kharitonov. If I give you a transfer function and with the variations, Then from that is you can, if the question comes on Carrot-Top, you have to find out those 4 polynomials, okay, like 4 extreme polynomials which are called Carrot-Top polynomial, and then whether they are Hurwitz. And if something comes from quadratic stability or affine quadratic stability, they are also, you have seen that those are descriptive kind of questions, right? There is one advantage if the question is descriptive type or derivative, if there is a mostly derivation, because the chance of doing calculation mistake is the minimum. Today we are like stopping here. Can anybody tell me that is after this what could be our next step or what can be our next step? We have learned the LFT and then finally we are proceeding toward learning the controller synthesis, right? So far whatever we have done, those are mostly analysis part. Analysis part means that is you are testing the robust stability or robust stability analysis. Yes, now that is we have to learn synthesis. Synthesis means controller synthesis. So for that is our main objective is to learn H-infinity controller synthesis. Again, that can be a stream feedback H-infinity controller, it can be output feedback H-infinity controller. So both of them we would learn and using the LMI based approach only so that you can directly apply. So for this LFT and H-infinity controller synthesis, you have to, if you wish to have a certain material, then the best one is the Carsten-Sierra's monograph. It is this compiled version of his lecture note. I will share that with you and I will mention the page numbers, okay? So if you see that is I have uploaded few things on WhatsApp. So that is mostly for this quadratic stability and then mostly for this parametric uncertainty. This is the paper which you have seen today that I have uploaded only page 2 and 3. You have to check, okay? Then uncertainty modeling, that you can safely study from chapter 7 of Stochastic book, okay? And then for LMIs and all other things, that is the Boyd Balakrishnan, the 4 authors book is pretty good. You only the chapter 2, 3, 4, 5, not the full content. You like go through the pages and try to identify which problem we solve here. Okay. And only one more reference I will upload, that is Carsten-Sierra's lecture notes.